So for this problem, we're going to take a look at the following line integral. Integral over c of x plus 3y dx plus 4x plus y squared dy over this curve c from 0, 0 to 4, 0 to 0, 2 and back. So I will consider this three separate curves. We'll do each of those three integrals and add them together to find the work. That will be my first path through this. So for C1, 0, 0 to 4, 0, the way you want to do this is you want to go with your starting point. 0, 0, then your direction vector. From 0 to 4 is up 4. From 0 to 0 is 0. So what I get here is my R1 of t is 4t comma 0. And that, of course, ranges as t goes from 0 to 1. My next example is from what? Is from 4, 0 to 0, 2. C2, 4, 0 to 0, 2. So we're starting at 4, 0. From 4 to 0 is down 4, so minus 4t. From 0 to 2 is up 2t. So again, negative 4, 2 is the direction vector. 4, 0 is the starting point. And again, I have this function R2 of t, which is 4 minus 4t, 2t. And this also goes as t goes from 0 to 1. We have our third version of this thing, C3, which is from 0, 2 to 0, 0. So start at your point 0, 2. From 0 to 0 is no change. From 2 to 0 is down 2. So my R3 of t is 0, comma 2 minus 2t as we go from 0 to 1. So I need to determine the line integral over C1, over C2, over C3, and we're going to add those together. So let's work on that. So we have all this information. X is 4t, y is 0. So we can make the substitution there. Now, dx dt, if x is 4t, dx dt is 4, which means dx would be 4 dt. Similarly, dy dt is 0, so dy is 0 dt. Then I can make my substitution and work on that integral. And you'll notice the second integral is all something times 0, so the second integral goes away. 3 times 0 is 0. 4 times 4t is 16t. So this entire thing becomes the integral as t goes from 0 to 1 of 16t dt, which is 8t squared over 2 as t goes from 0 to 1. Excuse me, 16t squared over 2, or 8t squared. So we get 8t squared as t goes from 0 to 1, which is going to give me 8. So that is the first piece. That's the integral over C1. Now let's go ahead and do that over C2. So doing all the substitution, x, 4 minus 4t will be x, y will be 2t dx. dx dt is negative 4, so dx is negative 4 dt. Similarly, 4x will be 4 times 4 minus 4t. Y squared will be 2t squared, and dy will be 2 dt. So let's make those substitutions. So there are the integrals, and let's simplify those and evaluate them. So here is the first simplification. So let's continue with that process. Here is the next simplification in terms of multiplying in the 2 here, and the 6t minus 4t is 2t, and then one more simplification. Now let's feed these integrals to technology and see what we get. So the integral of negative 16 minus 8t from 0 to 1 is negative 20. Then we'll go to the integral of 32 minus 32t plus 8t squared from 0 to 1, and I get 56 thirds. And negative 20 plus 56 thirds, you might be able to do in your head. That, of course, is negative 4 thirds. So that is what? That is the integral over the second curve, that second line segment. So we need to do one more. So here's the information we had. R3 of t was 0, comma 2 minus 2t. So x is 0, dx dt is 0. Y is 2 minus 2t, so dy dt is negative 2. Dx 0 dt, dy negative 2 dt. Let's substitute. And we'll see that this first piece, since dx is 0 dt, this first piece is just 0. So it comes down to the second piece, which gives me what? I have the integral from 0 to 1 of 2 minus 2t squared. So what is that? 4 minus 8t plus 4t squared, all multiplied by negative 2 dt, which gives us the integral as t goes from 0 to 1 of negative 8 plus 16t minus 8t squared. And again, I will ask technology to help me with this. You can see what we get. We get negative 8/3 there. So we've gotten all three of those. So we need to add them together now. So we have the integral over C1, C2, C3. We want the integral over C. So again, adding up those three pieces will give us that total amount of work done traveling over that triangle. We recognize these are actually elements of work. So we've got the work over these three paths. And as we put them together, what do we get? Over the first path, it was 8. Over the second path, it was negative 16/3. And over the third path, it was negative 8/3. So we'll add those together to get our total work. Correction, of course, that middle one is negative 4/3. So I have 8 minus 4/3 minus 8/3. What will that be? And we get total work of 4. Now that is challenging. Might there be a simpler way to do this? And the answer is yes. And even though this vector field is not conservative, we have a way that we can do this in a much, much easier manner. Which brings us here. And we will recognize that this is a simply connected, closed region oriented counterclockwise. So no holes in this region. It's piecewise smooth. The interior is always to the left. So this enables us to use Green's theorem. And that will be a simpler way for us to do this. So how does Green's theorem work? So if I have a line integral over some function m dx plus n dy over what? Over a simply connected closed region. Oriented counterclockwise. What can we say about that? Now, of course, if this is a closed region, the beginning and ending point are the same. So if the vector field is conservative, the work would just be 0. You would take your potential function, starting point and end point are the same. You'd subtract them and you'd get 0. Well, this Green's theorem works for us nicely if we have these conditions and we do not have a conservative vector field. So what does Green's theorem tell me? It tells me that work, integral over C of m dx plus n dy, where C is the border of the region, is the double integral over that region R of what? Of n sub x minus m sub y dA, or dy dx. So in this instance, we have m is x plus 3y. So I need m sub y, so the partial derivative of m with respect to y is 3. I have n is 4x plus y squared. So n sub x is 4. So the double integral of n sub x minus m sub y is 4 minus 3. dA, which is the double integral over R of 1 dA, would simply be the area of that region R. Well, what do I have? What do I have here? I have a triangle, and the area of a triangle is 1/2 base times height, which would be 1/2 4 times 2, which of course is just 4. So we get that done in mere seconds compared to parametrizing each piece. So again, in the event our curve is a boundary of a simply connected closed region that is piecewise smooth, I should have said that, piecewise smooth, oriented counterclockwise, then work for us is simply going to be the double integral over that region of n sub x, the second function with respect to x, minus the first piece with respect to y.